Hello, so this is homework 4 part C. Today we're going to be drawing and explaining the block diagram for a Smith predictor control system with dead time, and then we're going to derive the closed loop response of a Smith predictor controller system to change in set point and disturbance, and then simulate the closed loop response of a first order system using Colab. Oops. Okay, so this is part C, homework 4. So let's start, we're going to have our process blocks. So this is process, which can be simulated by our k times e to the negative theta s over tau s plus 1. And our process is going to be hooked to a controller, which we're going to call GC. So this is controller. And to estimate our process, we're going to need a separate controller in order to estimate our process. I already said that, but this will help us simulate the model for that. So this is going to be G bar P, which is a separate process. It's going to be our simulated process, or simulated model. Model, which we're going to represent with K bar over tau bar S plus 1, and our G bar P will be hooked directly to our controller, which is like this. Okay, so now what we're going to do is we're going to also account for our disturbance. So we'll make this, because we're going to need a little bit of space. So we're going to have our y component and our we're going to have our disturbance, which is GD. And to simulate our dead time, we're going to have our e to the negative theta s component, which is going to be hooked to a controller, which will be simulated through here, or directly attached. And then for our y set point, we're going to have another controller and our input, which this controller from our dead time will be, okay, it does not, okay, yep, will be directly connected to here, and that will conclude with our block diagram for our simulation. So we're going to be messing around with this y set point to get our output and disturbance and dead time. Okay, so for starting the second part, we've got our Colab set up. So I already got the library set and all the values that we need to use. And this tilde is basically just our K bar, tau bar, and theta bar that we used in our equation here. So for like the G bar P, which is going to be our GP tilde. So let's start with defining our GP, which we've already done actually with our process and our G bar P. So we just have it K times, or actually we'll K times negative theta, at least, yep, K times negative theta times S, oh wait, no, times EXP divided by tau times s plus 1. Then we're going to have our GP tilde, which is our GP bar, which we found to be K underscore tilde divided by our tau underscore tilde times s plus 1. And then for our t and y, we're going to simulate our GC times GP divided by 1 plus GC times GP lambda t is 1, and then n equals 1000, dt equals 0.1. That's not right. There we go. And then we're going to go back over to OneNote for deriving. Okay, so for our OneNote part, what we have is our process redrawn just a little bit simplified. What we're going to look at is this. So I drew a little envelope, which is going to be represented by GC times GP over 1 plus GC times G bar P times 1 minus e to the negative theta s, which for simplification reasons and make it easier to derive, we're going to call alpha. So in our main equation, y equals alpha times y times set point, or y set point. And again, this is going to be this. So to expand on this and to account for our disturbance and disturbance controller, we do d times g d plus alpha times y minus y set point, which if we do some simple math, we'll get y times 1 minus alpha, which equals d times gd plus alpha times y set point, which then we get y equals dgd over 1 minus alpha plus alpha over 1 minus alpha times ysp. And this is our derivation that we need. So we're going to go right back into Colab for that. Okay, so now what we're going to do is we're going to make a subplot that showcases our dead time, which basically what will happen is we're for a certain specified amount of time, which in our case it's 10.5 seconds. We won't really have any process movement, and then we'll see some action. So, or however you want to phrase that, ty equals y, mode equals lines, and then fig dot update score layout 400 with equals 600. There we go. So as you can see, our dead time shows that at 10.5 seconds, we get a sort of peak happening or a little bit of movement within our process, and then it starts picking up drastically. Okay, so now after this plot, we're going to also incorporate our derivation that we found. So with alpha, GC times GP divided by 1 plus GC times GP, GP tilde, which is multiplied by 1 minus exponential of negative theta times s. I believe that's it. And then, so our disturbance controller is equal to our process controller, and then ty. However, we're gonna do servo, and then so this will be simulated by alpha divided by 1 plus alpha and lambda t colon 1 n equals 1000, and then dt does equal 0.1, and then for dy, except this is disturb, it is basically the same thing, just a few differences, but for ease we're just going to do that. And our gd over 1 plus alpha, and then our lambda t is a little different. It's going to be t divided by 10 if t is less than 10, else 1. And that should be all the same, I believe. Let's see if that works. There we go. And then fig equals make underscore subplots, and then fig dot add, oh, not gif, fig dot add underscore scatter, where x equals ty equals y underscore servo, and then we're doing the same for disturb, so I did get that right. And let's update our layout and get the same as before. And that should work now. One sec. Okay, so found the problem. It's supposed to be theta tilde, not just theta. We're taking into account for our model. So what this graph basically represents is it's basically all of this, except we're moving our dead time, which we want to show that why dead time can be important, even though we see that our process is not really started for a while. However, if you remove that, you can see that it spikes and starts creating a bunch of different oscillations, and it's working towards steady state. However, it will take a lot longer. Whereas if you have dead time, it does not create those oscillations. It's more predictable, and it will reach steady state over time in a more smoother pattern rather than very sporadic and continuous oscillations between the same amount of time as the previous process.